My name is Natasha Coonan, and this presentation will discuss the importance and the different applications of calculus in electrical engineering. As a brief history, electrical engineering is thought to have first been mentioned by an ancient Greek philosopher, Thales of Miletus, in 600 BC. He first described static electricity. Many centuries later, it was finally recognized as a valuable branch of physics during the 1800s. However, in the late 1800s, universities began to offer degrees in electrical engineering, thus transitioning the subject from a branch of physics to engineering. There are now many fields of electrical engineering. These span from robotics to communication, software development, computer hardware, control systems, electromagnetics, design, optics, space systems, signals, and the list goes on. To study electrical engineering, an individual requires an understanding of algebra, trigonometry, geometry, linear algebra, differential equations, statistics, and most importantly, calculus 1 and 2. We are living in what is known as the information age, the computer age, the digital age, the technologic revolution formed by capitalizing on computer microminiaturization advances, according to Cleaver-Randy. You see, the evolution of technology in daily life and education allows today's society to have access to rapid communication and networking help. And guess who sits in the center of an ever-evolving society of electronics? The reason behind the evolution, the reason behind the internet, and the reason behind the electronics in your phone or your computer, you guessed it, electrical engineers. Electrical engineers have to manipulate mathematics on many occasions during their career, whether it is in something as interesting as Tesla coils or something as common as police radars. We know that calculus concerns rates of change. In circuits, something as easy as finding the first derivative is used to maximize power delivered in circuits. This is related to rates of change of circuits. Electrical engineers also look at rates of change in electrical power generation by using Faraday's law of induction, as well as the rates of change in transmission and distribution of electrical energy. For this, the Bessel function is used, which uses the second derivative and the first derivative. For this discussion, calculus will be investigated in three problems: linear differential equations in electrical circuits, Ohm's law to find the rate of change of a current in a capacitor, and Faraday's law to find the derivative of the magnetic flux in a rotating coil. For circuits, electrical engineers need to be able to figure out the current in order to monitor energy output. Circuits often concern volts, current, resistance, induction, time, and a switch. If the current is unknown, yet the values of the volts, the resistance, the inductance, and the time are known, then an electrical engineer, or in this case a Year 12 method student, can use a linear differential equation to find the current. This equation is L, the inductance, multiplied by the derivative of the current with respect to time, plus R, our resistance, multiplied by the current, which gives us the volts multiplied by the time. The following equation involves integration calculus within linear differential equations. Now consider the following problem. A battery supplies a constant voltage of 48 volts. It has an inductance of 4 henries and a resistance of 12 ohms. Given that I, the current of 0 equals 0, find the current of t and current after 0.5 seconds. We can then plug these into our linear equation. Therefore L we know is 4. We leave the derivative of I as we are trying to find I. Then we know that our resistance is 12, and we are also given the voltage at a constant rate. Therefore, 48 times time is just 48. We now need to compare the equation that we're using to the standard linear equation form. That is, y dash plus p of xy equals q of x. We're using the other equation because it's easier to use when working in terms of circuits. It's essentially the same. Y is the current, P is the resistance, and Q is the volts. Continuing on with the equation, it can now be solved. We will divide the equation by 4 to remove the coefficient of the derivative, giving us di over dt plus 3 times I equals 12. We need to then multiply through the equation with the integrating factor e to the integral of px dx, or, in this case, e to the integral of pt dt. We then sub in p, the coefficient of I, for 3. and get e to the integral of 3 dt, which when we integrate gives us e to the 3t, remembering that the derivative of e to the x is e to the x. We then multiply both the left hand and the right hand side through to get e to the 3t di over dt plus 3 e to the 3ti equals 12 e to the 3t. Now we need to simplify the left-hand side in order to integrate. First, we take the derivative and we move it out to the front of the term. Now we have d over dt e to the 3ti equals 12 e to the 3t. But how do we know that this is exactly the same as our previous equation? Well, to prove this, we have to use the product rule. If we use the product rule to find the derivative of d over dt e to the 3ti, v du plus u dv will give us our original equation. Now we have it simplified, we need to take the integral of both the left and right hand side. The integral of the derivative cancel each other out. On the right hand side, we now have the integral of 12e to the 3t. To integrate this, we just divide 3 through, the derivative of the exponent, giving us 4e to the 3t plus c, our constant of integration. Now all we have to do is solve the equation for I in terms of t, time. We divide both sides by e to the 3t to make the I solitary. So now we are left with I equals 4e to the 3t plus c, our constant of integration, divided by e to the 3t. The 4e to the 3t over e to the 3t cancel each other out, and when we rearrange our equation, it gives us I equals 4 plus c e to the negative 3t. We also know, relating back to our original question, that I of 0 equals 0, meaning our current is 0 and so is our time. So we then plug these in, and this gives us our constant of integration, which in this case is negative 4. We then plug this back into our original equation to get I equals 4 minus 4e to the negative 3t, which when we simplify gives us I equals 4, 1 minus e to the negative 3t. And this is our final equation for I. Now, if we want to find the current after 0.5 seconds, we simply just plug 0.5 in for t to get I equals 4, 1 minus e to the negative 3 times 0.5. If we are working with e equals 2.72, that will give us approximately 3.1 amps. On to the next situation, calculus and capacitors. Capacitors are used in many electrical devices today, for example, the flash of a camera. The current that runs through the capacitor is the derivative of the voltage with respect to time. Usually on circuits, one can control the voltage as it runs in and out. More voltage means more current. This means that the current is proportional to the gradient or the slope of the capacitor's voltage plot. So according to Ohm's law, the formula for a capacitor current is the derivative of the voltage with respect to time. Our last equation used the derivative of the current to find the current, which was awfully confusing and used integrals, but this formula is fairly simple. The results of the voltage are usually plotted on graphs. If one was looking at a voltage graph, sometimes it's easier to see the derivative. For example, consider having a graph that looks like this. This means that our voltage is negative 2 sine x minus pi on 4 plus 1. Now we wish to find the derivative, our current. So we use our knowledge that the derivative of sine is cosine. Therefore, when we find the derivative of negative 2 sine x minus pi over 4 plus 1, we have to use the chain rule. We can rearrange the equation to make it look a little simpler, and then we use the chain rule, which ends up making 1 minus 2 cosine x minus pi on 4 times by the derivative of what's inside the brackets, which just ends up being 1. This means that our derivative, or the current, gives us negative 2 cosine x minus pi on 4, which originated from the line minus 2 sine x minus pi on 4 plus 1. On our graph, we can now clearly see our voltage plot in comparison to our current plot. The final equation looks at Faraday's law. An electrical engineer needs to take into consideration voltage, current, and magnetic flux when considering rotating coils in power generation. In a magnetic field, if a coil is rotated, it will generate a current and a voltage. The voltage and current are related. However, when we're talking about Faraday's law, we also need to look at the constants that are related to the rotating coil. This is the area of the coil, the magnetic field, and the number of the turns. Faraday found that the amount of voltage created is proportional to the negative change in magnetic flux of a rotating coil with respect to the change in time given a particular current. Calculus! Consider a coil rotating in a known magnetic flux of 5 Webers, which generates a sinusoidal waveform. Using Faraday's equation, we need to find the derivative of 5 sine theta, remembering that the derivative of sine is cosine. Therefore, the derivative of 5 sine theta with respect to time is negative 5 cosine theta, where theta is the radial angle of the current. However, we're not finished because, as I said, when we are looking at current and voltage, we need to take the constants into consideration. This is written as NBA, where N is the number of coils, B is the magnetic field, and A is the area of the coil. These letters can just be written as X, an overall constant, which makes the equation look a lot simpler. In conclusion, electrical engineering may seem complicated, and for the most part it most certainly is, but I've proven that even in some of the most complicated concepts, easy calculus can be applied. Without calculus, therefore without electrical engineering, who knows where society would be today.